the great introduction there. Thanks everybody for showing up today, and Paul as well for always the nice introductions there. As Steve really mentioned here, today we'll be talking to you about Baratine. Baratine, it's something that we've been working on for the past 2 years. It's something that, as he mentioned, we're excited about. We see it as something that's going to be highly adopted in the Java community, brings real business values to the people who are building on it, who are utilizing it, and it solves a lot of the questions out there when it comes to building resource services, when it comes to building Java applications that are highly performant, that are distributed, and that are meant to be consumed by a ton of actual end users there. So what are we talking about? What's sort of the rundown of the slides deck that I have here for you guys? We're going to be talking about fast resource services. So we'll cover some of the basics of Baratine's in-memory services. We'll look at what it contains in terms of its database structure. We'll talk about the communication that Baratine does provide to you, the resilience and scalability, which are key points that people do want and do need within their services. And we'll also mention at the last topic, microservices. Once I'm done with the slides here, we'll take a short break, and we'll have Nam actually dive right down into some of the code, and just to show you how simple and easy it is to use Baratine and some of that true value that it can bring out to you. Okay, so to start off here, microservice. So just as a show of hands, how many people have heard this term lately in the news here? 4 or 5 of you. Anybody want to take a shot at some of the characteristics that you might describe around a microservice? I'll throw out the first one. Loosely coupled, for example. Seconds, anybody? No? David?
It's kind of breaking down the monolith way of building applications, where you have a lot of advantages in spreading functionality through different services, where you can scale bottlenecks, but you don't need to scale the entire application.
That's exactly right. Oh, you got more?
Yeah, you can actually build. You can build with a few platforms. You don't have to do everything in Java or in. Each service can be its own thing, and in general, you can do deployments that are really easy. So yeah, it's kind of a nice approach.
And he actually captured a lot of the things that I'm planning on talking about. I don't know if he wants to do the presentation. So highly concurrent, loosely coupled, able to deploy at once, able to be consumed by a lot of different programming languages, because there's a lot of programming languages out there. Some of the characteristics of what a microservice should contain should be asynchronous, non-blocking, fast, lightweight, another great term. And that's what we have today with Baratine. So what you're seeing here is all of that encompassed into an actual model. So the basic model of a Baratine service, an in-memory service, is that your Java code is going to actually now contain your data as well as the service itself. So taking a look at the model here, what you actually see is on the right-hand side, we have the inbox with requests coming in. Those requests, we'll get into the details of what clients they'll be coming from later. But the gist of it being that the inbox is going to be passing along those requests to the service. The service is going to be doing some sort of data manipulation, some sort of business logic on that actual request, returning something to the outbox there. And it actually gets returned on that same thread. Couple of points here to point out about this service is that when you build an application on Baratine, you're inherently going to get asynchronous, non-blocking, highly concurrent code without having to write synchronized in front of your methods, without having to use atomic locks. Baratine does that below the covers for you so that you focus only on writing your plain Java objects for the code itself. So that's a lot to say. What's Baratine look like in the field? On the left-hand side there, again, we have the traditional app server coming in. You might have a Python client. You might have a browser coming into the service. You can link Baratine right into your current architecture. So if you have a gateway database with your MySQL, or you have a SAP on the back end there, you need to integrate it. You can see the point of integration where Baratine comes into play there. So will Baratine replace your database? It's not meant to completely replace your database. It just means that you now can use the database for offline analytics, reporting, the things that will no longer chokehold your application when it comes to a ton of requests coming in and wanting to use and manipulate that data at the same time. Multitasking. So what we're talking about here, getting to the performance about Baratine, multitasking, because we needed another word for unable to focus on the task at hand. Anybody here good at multitasking? I'm glad not too many people raise their hand, because there's new research out that does show that everybody's bad at multitasking. That, you're actually 40%, you lose 40% of productivity when it comes to multitasking. And it turns out that CPUs are about the same when it comes to multitasking. When it comes to dealing with a lot of threads, you run into things like thread contention, you run into things like deadlocks, and you run into things like context switching, which are all costly and which are all hiccups when it comes to the actual performance of the application itself. So how is this something that we mitigated within Baratine? How is it something that we've addressed? There's a lot of methodical, the past 2 years, that's gone into the actual architecture of what we contain within Baratine and what we chose to leave out of Baratine. So one of the first points here to make is that the in-memory service that you write on Baratine is going to be uninterrupted performance. When we say uninterrupted performance, what we're talking about is that Baratine processes all of the requests in a single-threaded model. So you have a highly concurrent application in a single-threaded model. Your requests come into the inbox. The inbox there on that service is going to automatically batch and automatically queue that service through to the outbox. And again, that same thread is going to be reused. This arrow could actually come right around to the inbox there. And that same thread that comes in with the request is the same thread that's going to have those responses and the results at the back end of it. When we talk about CPU affinity, single-threaded means that you're not going to be dealing with the cache misses that you might have when you're context switching within a lot of multi-threads there. So your applications are going to perform a lot better. You're not going to have to worry about debugging tons of different threads that came into your application. So you've got 500,000 end users. You got a multi-threaded application. Something went wrong. Good luck at trying to figure out which thread was operating on which method at that time with the with the traditional architecture. Baratine's architecture, while there still may be a hiccup in your application, you can very easily track down the logical and sequential path of that single-threaded method that was actually executing at that time point.
What's the service doing in this case?
The service is any service. So you might look at the service, and we have some examples in the further slides we'll talk about. But in this case, we might say it's an auction service or it's a counter. So you're looking at taking in a request. The request might be something like, get my current count and return it. You have 500,000 end users who are all wanting to look at the current count or the current count of how many people are accessing your application at the time, or which methods are being used the most. And so the service is something that, in this picture here, is just the model of Baratine. The service contains the data as well as your operational business logic for that service, for your increment, for your count service that you may have. So, last bullet point there, batching. Batching is one of the main reasons why Baratine does perform as well as it does perform. In the traditional multi-threaded architecture, you'll have, for example, a synchronized method call. You write your synchronized method call, you write it once, comes in on a thread, and then it flushes. Then it hits the next method call. The next request comes in. It writes. It has a write method as well. Then needs to flush. And again, you have a new thread coming in. It needs to write something. It writes something and then flushes. And that's a model that, while you can't program it, while it is something that's usable and it's out there today, it's something that inherently cannot perform as well as a batch service. So with Baratine, the difference being in a single-threaded nature and everything coming in on the inbox, just to remind you again, everything on the inbox here, we have one thread that's processing the inbox. So the inbox looks and it says, okay, there's a write, let me go ahead and write this. I'm not going to flush yet because I'm the only thread that's working with this inbox. I can see if there's more work to be done. So there's more work to be done. Let me write again. You write for the third time and then flush. So flush is after the inbox is actually cleared of its data, or it's reached the threshold in that inbox batch size. What you have there is an example of automatic batching, where TCP can send 100 bytes as fast as 1 byte. Because every time you have a synchronized write and you have a flush, you're pausing and you're waiting. There is no communication within the multiple threads that are coming in. There's no way for one thread to know, is there more work to be done? Do I need to write this as the next thread that's going to come in, going to access that same object or data when you have a multi-threaded environment? When you have Baratine, it knows what's going to be manipulated. It knows the order that it's going to do that single-threaded in nature, and it knows exactly when it can flush, so you get that tenfold performance time looking at Baratine versus the traditional model. So again, all of the actual services will come in on the inbox. Inbox batches the actual request. 10 requests get sent as one, depending on what the request actually is. And you get that CPU affinity, that single threadedness, that high performance of the actual application that you're running there. And so what does this look like in terms of performance? What's the performance in context? Well, if you have a single end user client with a WebSocket where you're processing one request per actual per client, you'll see about 50,000 requests per second being processed. With WebSocket, when you're batching those results 10 at once instead of the one, you see tenfold times improvement. So you see 500,000 requests per second. Second sort of portion here that I haven't mentioned yet about Baratine is that Baratine contains the data base in the same JVM as the actual application. So there's no performance penalty for going to the database for the data that you're going to be working with. So in JVM messaging, we'll see about 4 million requests per second being processed when you have a service working from service to service within that same JVM. Maybe you have a service that's outputting log messages. Maybe you have a service that's batching and event processing. If it's within that same JVM, we're going to see basically sonic speed running as fast as possible. So that's the type of performance that we're talking about when it comes when you look at batching versus the single request multi-threaded environment. Resources. So one of the points we want to make here is that resources within Baratine is something that is locally owned. Every actual resource owns its own data. It's responsible for its own data. As I did mention, it's single-threaded, so it's very easy to look at the log scheme of what that actual resource was doing with the data. And we'll jump into some of the details in the following slides here. So resources, what are they? Resources, something that you might look familiar to you, they're REST-style URL address services. This is a model that presents you with object orientation. Data and the methods together, all processing within the same JVM, all processing within the same actual thread, allows you to get some of that performance that we talked about earlier. So what you're seeing here in that URL link that's very REST-ish style, you have the actual name of the service with an associated ID. So the actual example here is an auction. It could very much be a shopping cart. As you'll see later, we'll build an actual atomic counter that's distributed, it's highly concurrent, it's gets the benefits of asynchronous non-blocking code even when you're dealing with the actual data. There's only one resource that's going to be manipulating that data. It doesn't have to worry about thread contention with multiple threads working on that data. Resource service. So a service that manages resources is a resource service. Each resource is actually owned by one service. It can be saved to local disk. They're replicated, so in case an actual, you have a JVM crash or you have a server crash that restarts, your hardware fails, it's backed up and replicated so that data can come right back to you. We'll talk a little more about how it's replicated in some other slides here. And again, it's partitioned by the URL. So it's very easy to find the actual name of a resource by just looking at what the actual URL is. You'll get to the resource manager and begin to be able to call that resource and utilize the method calls, the the actual business logic that that resource does present to you. So what does it actually look like? What's required on your end to get some of these benefits? We have a plain old Java object here. So the resource service, you'll see the actual URL at the top there. It's annotated with resource service public to say that this is a Java object class that I now want to be available to the public. The method that you see there, the add modify is going to say that we're going to be saving this state. Public long increment again simply returns a counter to let you know the count of however you're implementing that. That's let you know the count of how many users are looking at your software or using your application, how many times a specific file has been accessed, and again, this simple service can be integrated with other services where you're looking at now a microservices combination to really get that decoupled, highly performant solution that we were talking about earlier. What's it look like in a picture? Well, we have, again, the actual inbox coming in on the resource service. We have a multitude of services there that are persisting their data into the, that are putting their data, I'll say that it's not actually persisted to disk yet unless you actually want it to be. But so for the time being, this model here is in memory. It's capturing the actual asynchronous non-blocking methods calls here. So as Steve mentioned earlier, majority of the applications out there today, when people are looking at using NoSQL databases, when they're looking at introducing data grids, caches to their actual architecture, a lot of the things that they're doing to get performance really is adding a lot of the actual complexity to the actual application. Baratine, every service is responsible for its own data. There's only a single thread actually writing to that data at the time, so there's no need to worry about thread contention, cache coherency issues, data migration schema. It's all in memory, it's all accessible, and it's all very much available to the resources that want to actually use them. So about that database, it's a store and retrieve. It's for storing and retrieving resources. So it's a key value store. It's asynchronous, as I did mention. It's a journal for performance and reliability. So the method calls that come in, and this is a database that's usually write only. So there's very little overhead for the actual journaling of it. It journals the performance calls and actually checkpoints them. So if your actual server goes out while you had requests being processed, you can very easily spin that service back up and pick up right where you left off without any sort of performance hiccups, without any sort of reliability issues. What happened? Well, you got the logs. You can look at the single-threaded logs and the output produced and very quickly dial down into what actually happened. Another point here is that if you have your services decoupled on separate hardware machines, one of those hardware machines go down, your application doesn't entirely go down. You might have a portion of your application not working, but you don't actually crash and lose your entire architecture versus when you have a traditional monolithic application server, that application server goes down, you lose everything. So we talked a bit about what the resources are, talked a bit about some of the performance that Baratine does bring. Next sort of question in line would be, well, what sort of communication does Baratine have? I did say to you guys earlier that there's a lot of end client availability, and we'll take a look at how that's made possible. So the protocols, using a service. Picture first, because pictures are always good. So you see here we have Node.js, we have Java EE, PHP, front-end scripting languages, Python. They can all communicate and call into that service. REST is for the simple client like curl. Baratine provides a REST interface. Ajax RPC, WebSockets, when WebSockets are available because they are the best communication, fastest communication we have out there, will provide better performance. And of course, if we don't have the availability of WebSockets at REST, we can always fall back to the HTTP long polling there. The actual content of what's getting sent there between messages, what does it look like? We've introduced a new protocol called JAMP and HAMP. JAMP is JSON over active message protocol. HAMP is Hessian over active message protocol. Hessian is simply JSON in binary format. So hashing's for that ultra high performing service that you need sending binary data. JSON for easily readable, easily consumable by all types of end user clients. Almost every language out there today supports JSON. So you have that automatic communication. And we added some structure to that to give it, the sort of dumb pipes. We don't want the business logic stuck in the pipe transferring it. We just want the message to get to its end target and then provide the business logic. Decoupling the actual business logic application from the core implementations, what microservices is all about. So we also provide a gateway service here. So Baratine, as we mentioned, there's a lot of great features, and maybe it's something that you want to take advantage of today, but you don't actually want to completely rewrite your backend. You want this data to be used, but maybe because the way the team is split up, maybe because of how much actual legacy code you have, it'd be a lot easier for you to quickly integrate by simply placing a service interface onto that Hibernate, onto that JPA, SAP, whatever backend model that you might have there. So one of the things you can do then with Baratine is you can use Baratine as the actual operational data, use Baratine to respond to the service, and you could stream the analytics of that service, of that data and that services to a backend. So now your analytics is decoupled from your actual service usage, so your service usage can skyrocket. You get the performance, the productivity from this, and you no longer are going to be held back by the actual database. And then just loading data example. So using relational databases, again, this is a way that Baratine can quickly interface right into the actual backend that you currently have with your system. So resiliency and scalability. These are terms that are thrown around, or they're out there in sort of every buzzword, every article you read says it's scalable, says it's resilient, but how do they actually accomplish this? One of the things that we're doing with Baratine is really pushing forward the single-threaded model and nature of it, which does mean that if you're using APIs such as EJB, such as JMS, JCache, JSF, those APIs are inherently blocking APIs that don't actually mesh with the asynchronous nature of Baratine. So again, at that previous slide, when we had looked at the performance of what Baratine gives you with an actual application with blocking calls, you're limited unless that actual architecture, underlying architecture, is something that truly supports resiliency and truly supports asynchronous scalability in the decoupling of its services. So how does Baratine accomplish this? Well, we have every resource partitioned by a URL. We have the data within that resource replicated, and we have backup servers available whenever the current server may go out. So it's nothing that you have to worry about. It's nothing that you have to pre-program into your application in terms of the failover. Baratine, if your current client is connecting to, let's say, we'll call this service 1, it's connecting to service 1, it's using some data from service 1. Service 1 is on a machine that somebody walks by, unplugs it, walks by, kicks the cord off the wall, it gets unplugged. Baratine very easily knows what the actual backup server with that same data should be. So what it will do is it'll put that server as the new response to that client and send that data back over to them. When that primary server does come back up and primary service is back available, Baratine then moves that current server back to the backup nature, and the current server takes over as it was previously operating there.
How does it know? Does that heartbeat the server or so?
It heartbeats the server. So yeah, it's actually managed by, how does it do that? It's managed by Bartender, which if you guys are familiar with Zookeeper, Bartender is our own implementation of Zookeeper. Why didn't we use Zookeeper? Maybe now I might get into some of the details of that, but let's say for efficiency reasons, because we know exactly what the payload is that we want to be heartbeating throughout the cluster, and we know what extra efficiencies we don't want to be sending throughout the cluster. So Bartender manages failover and scaling. It's Baratine within a cluster. It's symmetrical, if you guys are familiar with the gossip protocol. It's service pod topology. So Bartender is responsible for saying, okay, this service is located at this URL. I can take a hash of this URL, I can mod that hash, and I can get the virtual location of that service. Based upon that, Bartender keeps a management of that virtual and the actual physical location, and very easily can, from any cluster, any service that's hit within the cluster, can direct that request right to the service holding that data. So this is something that's meant for the cloud, for the dynamic servers, for Rackspace, EC2, those sort of environments. And again, this is something that was built in-house to inherently support the failover and the scaling of Baratine. Service journaling, we talked briefly about this earlier. So service journaling is meant so that when something goes wrong, because everybody here is in the software world knows that things go wrong at times, you need a way to recover from that. Baratine will journal your services. It'll save the index and the method calls, and it can recover automatically on a restart. Again, it's replicated for failover, so it's nothing that you have to worry about in terms of losing data when something goes wrong. Services. So we talked about what Baratine is and what it does. Let's look at its components and mention one of the key facts here. Baratine is 7 megabytes in file size. So the term lightweight's thrown out there a lot. Lightweight, WebSphere, is WebSphere lightweight? Is WebLogic lightweight? It's really an opinion, but I think we all can agree that 7 megabytes is pretty small. There's probably smaller than some of the actual applications that you guys have on your smartphones. So within this, what we packed into 7 megabytes is we packed in the key value store database, we packed in the journal, we packed in the communication for Champ and Ham. We have Bartender managing your services within the cloud as well as the Baratine file system. We have a service registry for registering services, and we also have a web server. Part of the reason why we've done the things that we've done in terms of what Baratine contains and why it does that is that performance, as Steve mentioned, is one of our key concepts, something that we always go back to. So Amdahl's law, I'm sure you guys have heard of it in the past, is the speed of a program is using multiple processes in parallel is limited by the sequential fraction of the program. So what that's actually talking about there is that you're limited to the portion of your application that must be sequential, that must be serialized. So you want the portion of it that can be parallelized to be run as fast as possible on multiple actual CPUs. That portion that cannot be ran in parallel, that must be sequential, you want that portion to run as fast as possible, because that's always going to be the end bottleneck within your application. So serial and parallel is something that we've incorporated into Baratine in terms of looking at the basis of mechanical sympathy. So we partition your resources for parallelism, because today we have a lot of multi-core CPUs that can do this processing. We have the single CPU efficiencies that I talked about earlier. The single threaded nature means that the portion of your code that has to run sequential is going to run as fast as possible. How are we doing that? Well, CPU affinity means that that thread is going to have some knowledge within that CPU that's been working with that thread, so you won't have as many cache misses, you have no context switching. And again, batching means we can process 10 requests, 10 requests is one. So the same hardware can handle 10 to 100 times the number of requests. Less vertical scaling to manage, and put simply, it's doing more with less. It's what Baratine's all about. So Baratine services, they are loosely coupled. These are some of the terms that developers might want in terms of, or managers that might put on the developers in terms of the applications they're building, are that the application should be asynchronous, it should be event-driven, it should be agile, should be non-blocking, and the basis of what we have here: responsive, resilient, event-driven, and scalable. It's really where we focus in Baratine at. Baratine is something that encompasses all of these, and it's really the new wave of applications being built out there today, are that loosely coupled systems are systems that can be worked on by multiple developers. Loosely coupled systems, resilient and responsive systems, are ones that when a portion of the application goes down, your entire architecture is not doomed for. Non-blocking, because of course you does not want to be writing non-blocking asynchronous code. So microservices, and I want to thank David again. Oh, there he is. For the great definition earlier. But we'll talk a bit about microservices and you know why they're sort of picking up so much steam and so much attention in the industry right now. So microservices are really code that adheres to the principles of SOA. SOA obviously is not a new term, so it first came out in, I guess, early 2000. A lot of it was around enterprise Java beans. Not so sure that EJB was the greatest implementation of the principles of SOA, because you were left writing bean interfaces, home interfaces, deployment descriptors, a lot of the things, filler code that you're not even actually using. So what are the principles of microservices that really matter? It's all about faster development. So we're not introducing new languages for you to write in. Again, you're only writing the plain old Java objects. You're not introducing any I don't even have a complexity here. You're not introducing data grids. You're not introducing caches. You're not introducing those extra levels of an architecture just to get a microservice. You're instead focusing back in on the object-oriented nature of what Java was meant to be, and achieving that scalability, achieving that ability to easily debug your service there. And again, we talk, I'm not sure if you guys have read the book by Martin Abbott and Michael Fisher, but in the book they talk about the x-axis, the horizontal duplication of code, service splitting, scaling by cloning that service. They talk about the z-axis, the data partitioning, so scaling by splitting the similar things. The new one, the y-axis, that's the functional decomposition. That's the decoupling your services, splitting by things that are not similar. So where are we now? We have out there a lot of buzzwords: microservices versus SOA. We have SOA 2.0. We have domain-driven design, reactive manifesto, silos development. They're all really trying to say the same thing. We have, a lot of new messaging queues. We have a lot of new NoSQL databases out there today. In fact, Facebook just revealed Apollo. I'm not sure if anybody's had some time to take a look at that. They said they're not using it in development, but they put it out there. Why is this coming up? Why are we sort of reaching full circle here? Well, part of the problem is that, and Steve Jones talked about this back in 2006, that the business, they looked at using the business value over your actual technical strategy within your product. They talked about the strategic goals and the project-specific benefits of what the code is actually meant to do. Martin Fowler actually is probably the latest one to coin the term microservices, had a great piece on it. Steve Jones sort of took issue to that because he says, well, he's like, hell, I even wrote a book that talked about how to model, manage, and set up teams around this approach, the SOA Manifesto. Talks about key principles behind SOA from a big group of practitioners. So, the point is that we've known what type of services we wanted to build. We haven't had an architecture that's been built specifically for them up until this point. Baratine is the architecture that's meant specifically addressing these issues of SOA principles with underlying technology behind them. So let's take a look at some brief example code again. So again, we have the thread request coming in on the inbox. We have the service here. It's going to be doing whatever business logic, whatever actual service you want to do within that. And we have that outbox result coming back in on that same thread there. Here we have on the client side, an implementation of a resource service, my service. It's simply returning the string passed to it, saying hello, argument passed to it. You can also provide an interface for that. You'll notice that the actual client doesn't actually implement the interface. And why is that? Well, a couple of reasons for that. You can have actually two teams working on the same implementation of code within Baratine. They can provide that implementation and the actual server side of the service, as well as an example interface as to what we want done. But let's say the interface, as in this example, is one that's, well, that one's returning something, so we have a blocking interface. We have an actual implementation class that's not using it, so you're decoupled. There is no client library that you have to rely on. You're allowed to, implement the interface as you choose to, or implement as you see fit within your actual environment there. So
Is the single thread model, is it single thread per service, or how does it work? Because I assume, so you have your input queue, the requests are coming, they're queued up, and then eventually you're distributing that from maybe message queue or event queue.
Right.
So your service bus, it's something, some single thread or maybe some multiple thread going on, maybe there, I don't know, should be grabbing one request at a time and directing that on one specific service. Is it one thread per service at that point?
It is. So there's one single thread actually consuming the inbox for that service. It's relaying those onto, if you're familiar with the disruptor, Pat Elmix's disruptor, it's sequentially serializing those method calls to that request in an order there. It then traverses the request there and allows you to get that sort of single-threaded nature and response back to the request coming to it.
Okay, obviously one natural issue that you still have some sort of bottlenecks if something goes wrong in the, or maybe a blocking call within the service itself. Same service requests should wait at some point for that process to be completed, right?
You would think, and actually you may, depending on how you write your application, but the thing about Baratine is that usually when you're going to be blocking on a request being made to a service, because there's multiple threads accessing the data for that object. Baratine is a single-threaded, single writer for that data that's owned by that service, so there's no contention in terms of multiple requests coming in to access that actual data object within your service.
But let's say you're accessing an external resource, maybe database. Maybe it's taking so much time to consume data, to get the data.
Right.
It's going to block actually. So therefore your other requests for the same service queued up still, actually, still in the queue, waiting.
Right. In those cases, when you're looking at integrating with the backend service that needs to do some computations to bring back that data, you're going to be looking at a result of a future return to that service. So the future's return to the actual service, the sequential calls are still called, and their results are futures as well, depending on what actual is going on within the application. And there's a diagram in a few slides from here that'll show some more of that.
Another question comes to my mind. You mentioned parallelization, you talked about the Amdahl's rule. Obviously, there are some embarrassingly parallelizable algorithms you can think about, and you need to extract those sequences. Those are actually sequential processes that you need to follow in order to accomplish the parallelization and then come up with some speed up.
Right.
So how do you handle that parallelization internally?
Internally, the parallelization is dependent upon the application code that's calling into it. So if you recall that the sequential portion of the code that cannot be ran in parallelism is then batched in sequential order, so you have that maximum speed up, but you're still limited by that sequential order. So you will always be limited by the portion that can't be ran in parallelism, but that portion that can be ran parallel will be ran parallel. Your sequential order will be batched and ran as fast as possible, and then that method will return from there. And great question, by the way. Baratine benefits. So combining data and service, it's something that we call resource services. It's also been called object-oriented programming. The highlights of what Baratine provides for you is that we provide, one, we are eliminating the actual bottleneck of your database for those services. We're also providing to you any way to consume those services as you like. So writing a non-blocking asynchronous RPC service is as simple as writing a Java class. You can write an asynchronous, non-blocking, highly concurrent, available application in an afternoon because you don't have to worry about any of the atomic clocks. You don't have to worry about the synchronization. The performance is going to be as fast as possible. Baratine's taking care of those things for you. Integration with blocking, as we did briefly talk about. When the service does need to block or does need to wait, we're looking at passing back a future that the service will still process, comes back on that same thread, wakes the future, and then passes the result to it. So here you see the server-side example code of that earlier hello, the example main there is the hello service that we were using there. So when you do have to integrate and when you are actually limited, again, you are going to be limited by the performance of the future and the blocking, 186,000 requests per second. Obviously, if you can, it'd be better to rewrite that service entirely so that all the data is held within the JVM, within that actual service itself. And you'll be reaching 4 million requests per second, which is pretty good performance on some real basic hardware there. So related architectures, Steve talked about why we've been doing this, why we spent the past 2 years developing these things, what's going on out there. There's a great actual presentation on InfoQ. His name is James Lewis, if any of you want to watch it. It's a microservice actual presentation. And he talks about the principles of microservices and implementing it within their architecture. The problem is that when it comes down to actually writing it and having to use some underlying architecture, what does he end up with? Well, he ends up with an embedded Jetty. He ends up with Pico container for dependency injection. He still has Hibernate, so think about a microservice that's still going to be using the traditional backend Hibernate. You're probably not going to get the best performance that it can get. Abdera for Atom. He has smoothie charts, metrics, and he also has graphite. So there's, what does that show to you? What does that say? It says that there's no architecture out there specifically for microservices. You have here a combination of some of this would be considered, really an advanced architecture. They're utilizing Redis, very fast messaging and data caching. They have Node.js service at the front end for their WebSocket. They have a load balancer. They plug all this into their backend data layer. Is this now an architecture that's scalable? Is this an architecture that's easily maintainable? There's question marks surrounding that. When you're adding in WebSocket, Node.js server, are you a JavaScript expert? If so, great. If not, then you have people on your team who are no longer going to be as participant in the code because they don't understand the portion of what goes on in that front side there. We don't impose any restrictions with Baratine. You're simply writing plain old Java objects, so you have more contributions working on that same project there. Related architectures, again, we talked about EJB, JPA, JSF. Those are APIs that really were designed when we didn't have the prolific multi-core CPUs that we have out there today. It's not that EJB with great intentions, EJB 1 and 2 kind of drained its excitement, I guess, from the people willing to use it. By the time EJB 3 came out, you had things such as Springs, such as Juice that you could use, so there wasn't the great urge to go back to something that really ruined a lot of companies' projects. What is a comparable architecture to Baratine? Well, you can think about if you had an ESB to sort of withhold some of the business logic across your service. You had a data grid because you need the data accessed across in memory. So obviously you have a cache. You have a NoSQL database. You have some sort of asynchronous API. That's a pretty complex architecture there that is in a way would accomplish some of the things that Baratine does, but it's just something that is more of a just part components thrown together versus something really methodically programmed and methodically developed for resource services. Here we have actually Netflix's backend and they talked about, you know, if you're looking at, they talked about redoing their backend architectures. We had backend services and dependencies here. We have the actual different end user devices here. So I think one of these are Xbox, one of these are home, one of these are browser, Android. It's something that's now available to each end user component, but again, you have one huge backend cloud, so you can imagine the Baratine dependencies being one where if they integrate Baratine here, integrate Baratine here, integrate Baratine here, you have a single way of each service, each endpoint client owning its data. You have a way to pull that data for some real-time analytics and get very usable and readable business value out of the architecture that you're using there with Baratine. So Baratine and existing code, you know, this is something that we briefly talked about earlier, is this is an architecture that, yes, it's familiar, it's deployable. I'm sure there's architectures like this that are out in Amazon's EC2. It's testable because obviously people are writing JUnit tests for this sort of architecture. Is it maintainable? Is it scalable? Well, it's out there, it scales, it's being maintained. Can it be done better? We would argue that yes, it could be done better with an integration of Baratine. That would actually put me right at the 8 o'clock mark in a transition. So we'll break here, and when we come back, we'll have Nam actually dive right into some of the code and show you just how easy Baratine is to use.